So first, I'd like to thank the organizers for the kind invitation. It's my great pleasure to give a talk in this workshop. And I would like to apologize that I'm not able to join in person because it's an exam week at the US this week. So today I will discuss some of the small scale formation aspect for the Boussinesq equation, which is the equation that is describing the movement of fluid under the influence of the gravity. This is the joint work with Alexander Kiselev at Duke University and my former student, Jamie Park, who is currently a postdoc at University of Basel. So let me start with introducing what is the Boussinesq equation. Let's try to imagine that there is a density of the incompressible fluid, which we are going to describe by rho. So throughout the talk, we are going to work with the 2D case so that x is in the two-dimensional domain, and u, it denotes the velocity field of the fluid. Okay, so for the spatial domain, we are going to assume that it is either the whole plane R or the periodic domain, the torus T square, or we can also denote it as a strip, which is the periodic in the horizontal direction, and it has the upper and lower boundaries. Okay, so in all of our theorem, we're going to work with one of these domains. And the 2D Boussinesq equation is a system of equation that describe how is the density and also the velocity field of the fluid evolving in time. So the first equation denotes how the density is evolving in time. It says that the density is transported by the velocity field u, and other than that, it's not doing anything. Okay, so there's no diffusion on the density side. And as for the velocity field u, throughout this talk, I'm going to work with the incompressible Boussinesq equation, which means that the divergence of this velocity field is equal to 0. Okay, and here I'm putting a picture on just the illustration of an example of an initial density. Throughout the talk, I'm going to use the red color to denote positive rho and blue color to denote negative rho. Okay, so notice that negative rho doesn't really mean that the density is negative. We can think about the 0 value as the mean density. So red and blue is just relatively whether the density is heavier or the lighter than the average density. Okay, and the second equation here for the U equation, it describes that, so it basically says that the fluid particle obeys the Newton's law. So it's going to be along the trajectory, the acceleration of the fluid particle is proportional to the force, where the force is given by the pressure term, and also the so this rho E2 term, this is the key term that is coupling the density and the velocity together. It says that so the gravity is pointing downwards. Okay, so like in this picture here, because the mean density is equal to 0, so the red part will be relatively experiencing a force that is pulling it down, and the blue part is experiencing a force that is trying to pull it up. And also, so the last term here is the viscosity of the velocity. So we are going to work with both of the cases, either the viscous case where the viscosity coefficient is positive, or the inviscid case where mu is equal to 0. So in both cases, our goal is to prove that as time goes to infinity, so the solution can have some small scale formation. So it means that either the density rho or the velocity u is going to have some rapid change in the spatial variable. So that can be measured either in the CK norm or in the Sobolev norms. Okay, so that is the problem setting and the equation. So next, I'm going to first consider the viscous case, and I'm going to briefly review what is previously known about this system of equation. So for the viscous case, the global well-posedness of regular solution is known, namely for the spatial domain being the whole plane. It's known that so when the initial condition is in certain Sobolev space, whenever the exponent of the Sobolev space is bigger than a certain value, there is a global regular solution. Okay, so there has been different global existence results depending on the Sobolev spaces using. But for those of you that are not in PDEs, you can basically think about it as long as initially both the density and velocity are smooth, then there exists a solution for all times and it remains smooth for all times. Okay, and similar result is also known if the domain is a bounded domain. And in addition to these global existence results, people also want to know that, well, for these norms that are measuring the derivative of these solutions, how fast can they grow in time? So in the previous literature, there has been a couple of the upper bound of these Sobolev norms. For bounded domain, so Ju showed that the Sobolev norm can grow faster. So the upper bound is this function that is faster than the exponential function. And Kukavica and Wang have improved the bound and obtained that for bounded domain, so their upper bound on the Sobolev norm H1 is exactly an exponential function. And the W2P norm of U is bounded for all time. So which means that the second derivative of U will have its LP norm bounded for all time. And then in the whole space, they get some upper bound that is faster than exponential. And more recently, Kukavica, Masad, and Zain has improved that bound to something that is even smaller. They showed that the H2 norm of the density can be made the upper bound can be made to have an arbitrarily small growth rate. And the same thing can be said for the H3 norm of the velocity field U. Okay, so notice that all of these estimates deal with upper bounds of solutions. And a natural question is that, well, so for these upper bounds, no matter they're exponential or some exponential with a small coefficient, can they actually be achieved by some solution? Okay, so we are wondering that, well, what about the lower bound? Can we construct some example of solutions that actually have their norms grow to infinity as time goes to infinity? So, so far in the literature, the only results that deals with lower bound is established by Brandeis and Schoenbeck, and their result is as follows. They say that, well, let's consider the whole domain R2. As long as the initial density does not have the mean zero, so you can imagine that, suppose the density is equal to zero everywhere, and with this heavier portion of fluids that has a bigger density. Okay, so what happens is that due to the gravity, this part with the heavier density will be dragged down. And then the more that they go down, that is driven by the gravity. So by the energy conservation, the potential energy will be converting to the kinetic energy. So the more that they go down, the faster that they will become. And this goes into a feedback loop. And they show that the L2 norm of the velocity is going to grow in time, like exactly comparable to this t to the 1/4 power. Okay. However, this is due to potential energies keep converting to kinetic energy. So this heavier portion of fluid is going down faster and faster. It does not necessarily imply that the density function itself, when we are looking at its spatial derivative, it needs to have any growth in its derivatives, right? So far, we are not aware of any example of infinite time growth of some Sobolev norm of the density itself in the literature, and this motivates our study. So together with Sasha and Jamin, we proved the following results. For the time constraint, I'm only stating the results for the torus case, but we also have a similar results in the R2 case. So for the viscous setting, let's consider the domain being a torus. And we show that as long as the initial conditions satisfy the following two conditions, one condition is about the symmetry and the other condition is about there are certain sign assumptions, then the smooth solution, which we know exists for all time, will satisfy the following bound here. Okay, so this bound means that the H1 norm of rho will be growing to infinity along a diverging subsequence of time, and they will be growing to infinity with this growth rate that is at least polynomial rate of power 1/6. Okay, so it means that these kind of solution indeed have these small scale formation in the sense that their H1 norm is growing to infinity with some polynomial rate. So our assumption is as follows. We assume that both the density and the initial velocity is going to satisfy some symmetry condition. So in terms of the density, we assume that it is even in x1 and odd in x2. So and for illustration, it can look like this. Okay, and as for the initial velocity, we also assume that the horizontal initial velocity satisfies this odd even symmetry, and the vertical velocity satisfies the even odd symmetry. And it is well known that whenever the density and the initial velocity satisfy those symmetry, they will be preserved for all time. Okay, so that is very easy to check. And another thing that we assume is that in the upper half of the torus, the initial density is non-negative, and therefore on the lower half, because of the odd symmetry, they will be non-positive. And on the vertical axis, we pin down this value of the density to be 0 initially. Okay, and notice that this is also something that will be preserved for all time. Because by the symmetry of the velocity field, we have that, this vertical line and actually the horizontal line, they will remain streamlines for all time. Okay, so it means that if a particle starts here, they have to be live on this vertical line for all their life. And therefore, because the density is preserved along the particle trajectory, rho will be equal to 0 for all the time. Okay, so that is clear. And one remark that I would like to make is that under these assumptions, we will prove, so in the next slide, I will be briefly talking about the proof strategy. So under these conditions, we have proved that the global in time solution must have at least this growth rate. And one might wonder that, well, how far is it from how far away is it from sharp rate, right? Because previously for the upper bounds that I showed you, they're all exponentially growing, but this is like polynomial rate, and actually it's like a sub-linear power. So even though we don't know whether the rate is sharp, in terms of the power, we guess it's probably non-sharp, but it's the best that we can make. That being said, we can show that under these assumptions, it's actually impossible to have this norm growing exponentially because due to the symmetry condition, we can show that the H1 norm actually has a refined upper bound, which is lower than these exponential bound. So it is e to the ct to the alpha, where alpha is some number between 0 and 1. Okay, so it means that the actual growth rate is somewhere between polynomial rate and sub-exponential rate. We don't know which is actually the case. And another interesting thing that I would like to remark is that even though we are able to prove that, well, the solution must satisfy this estimate saying that's the H1 norm, which means the first derivative of the density will keep growing as time goes to infinity. But we actually don't know as time goes to infinity what whether the density will be converging to something or not. So intuitively from our life experience, if we are starting our initial density in this domain, where the red part is driven down, the blue part wants to float up, then the configuration with the least potential energy would be that the red parts try to get as low as possible, the blue parts try to get as high as possible, but they cannot cross this horizontal line because of the symmetry, right? We are actually not able to prove that as time goes to infinity, whether the row really converge to this right picture or not. So it's because the actual situation is more complicated than this. Other than this steady state, we also have infinitely many other steady states where every horizontally stratified density is with zero velocity actually is a steady state, right? So how do we know it will converge to this one with the lowest energy rather than converging to some other thing? So the asymptotics as time goes to infinity is still open. Okay, so that is a comment about the statement of the theorem. And I would like to just briefly comment on the proof. The proof idea is by carefully looking at a couple of quantities together. And one important quantity that we are going to consider, which is motivated by the fact that the Boussinesq equation is driven by the gravitational force, is the potential energy. Okay, so the potential energy is just the energy that we learned in the high school physics class. It is the density times the height and then integrated in the domain. And it also has another counterpart that is the kinetic energy, which is the integral of the velocity field squared. And it is well known that when we are adding these two parts together, they form the total energy, which as we take the time derivative, we can check that it is decreasing in time with this coefficient here given by the viscosity coefficient. Okay, so that means because the total energy is decreasing and it is bounded below because it's both the potential energy and kinetic energy, they have a very clear lower bound. It means that we have, as long as the viscosity coefficient is bigger than zero, this integral, if we integrate this gradient u squared on for all the time from 0 to infinity, we know that this integral is going to be finite. Okay, so that is going to be an important fact that we are going to use in the proof. And now we are going to track the evolution of the potential energy itself. So basically, we want to show that if the solution doesn't have the density doesn't have its H1 Sobolev norm growing with this polynomial power, then something will go wrong. Okay, so the way that we are going to do that is to track the second time derivative of the potential energy, where we are having these three terms on the right-hand side. And so if we assume that, so at the end, we are going to prove that the H1 norm of rho is growing like some power, but in this talk, let me try to prove something that is easier. So if we are going to assume that for some reason, the lim sup is bounded, then we look at all these terms on the right-hand side. Okay, so for this B term here, we are going to use Cauchy-Schwarz to relate it to the L2 norm of the gradient rho. And then we are going to have that, well, if this lim sup is bounded, then this time integral of B cannot grow too fast. Okay, so this is one thing. And another thing is that there is this very scary term A here, but in fact, this is not bad because for this coefficient here, it's relatively easy to show that it is bounded. And then the rest of the term will be bounded by the integral of gradient u squared, which we know that it is bounded by a finite number. Okay, so the time integral of A will be always a bounded number in time. Okay, so now our strategy is that we want to integrate this equation from time 0 to time infinity. And then if this limb soup does not grow, we want to get a contradiction. Okay, so the key contradiction is going to happen in the time integral of this last term, which I colored in orange. Okay, so suppose this limb soup is less than infinity, we have obtained that the time integral of A is finite, the time integral of B is t to the 1/2, and therefore the time integral of the orange term has to be also bounded by t to the 1/2, which means that on average, this inside term needs to be decaying in some way, right? Like t to the -1/2. But is it going to decay or not? So the next key observation, which we do it by, it's not a hard proof, it's basically just a Fourier series argument. And here it's the time that we are going to use crucially the fact that we set rho to be 0 on the vertical axis, and this property is true for all time. Okay, so the idea is that, well, as time gets large, we know that this partial 1 of rho will have its negative Sobolev norm to be super small. Okay, what this means is, intuitively speaking, it means that rho is very close to some horizontally stratified function in the distribution sense. And now we can try to picture that if I give you any of these functions, I tell you that, well, in the weak sense, it's very close to something that is a horizontally stratified function, but my function has a 0 value on the vertical axis, then it's not possible to have such a function unless the function has really quick change, really rapid change in the x1 variable across this line, right? So this can be proved rigorously in the sense that we can actually relate the positive Sobolev norm of rho with this negative Sobolev norm of partial 1 of rho to get that, well, if this right-hand side is small, then my h1, if this h-1 norm itself is small, then my h1 norm needs to be huge in some sense, okay? But that is contradicting my assumption that I'm assuming the limb soup of the h1 norm is bounded. So that is the idea where we get the contradiction to show that the limb soup has to be infinity. And if we try to do a more careful argument balancing the power, we can actually get some kind of polynomial growth. So this is one part of the argument which shows for the viscous case. So the solution is global, but the h1 norm of the solution will be growing in some way. And then for the Inviscid case, so we work with the density variable and also the vorticity variable. And then in this case, for smooth initial data, whether it can have a blow up in the torus or in the whole plane is still an outstanding open question. And people care about it, not only because the 2D Boussinesq equation is interesting by itself, but because it's also related to this equation is known to be closely related to the axisymmetric 3D Euler equation. But in the presence of boundary, so there has been many exciting development on the finite time blow up, namely, so Ho and Luo first got some convincing numerical evidence that blow up can happen at the boundary of the domain. And then there has been some work with blow up in the domain with the corner, or blow up with 4 solutions that is not smooth, but belong to the class of C1 alpha. And so in some recent works, there are numerics for the approximate self-similar blow-up solution using the physical informed neural network. And also in the very impressive work by Jia Chen and Tom Ho, so they proved that stable, nearly self-similar blow-up for smooth solution can happen, where they use a very nice combination of analysis together with computer-assisted estimates. So with Sasha and Jameen, we want to see that, well, whether there is any shorter and more intuitive idea for us to maybe not to get a finite time blow up, but at least get some kind of infinite in time growth. Okay, and then our result is as follows. So if we are looking at this setting with a boundary, then as long as we put heavier fluids up here and lighter fluids near at the two ends, then you can imagine that, well, the gravity will be driving down in this way, and it's trying to float up along the two sides. Right. So, and then we prove that, well, as long as we work with this initial data setting, then during the lifespan of the solution, because we don't know whether there will be a finite time blow up, but as long as the solution still exists, then all these norms will be growing in the sense that the vorticity's LP norm will be growing like this, which is the super linear growth. And the maximum velocity will be growing at least linearly, and the density will also have this growth. Okay, so the proof is a very short argument. It's a short and soft argument. It's based on an interplay between various monotone and conservative quantities, which I am going to skip due to the time constraint. And one last thing that I want to share with you is it's a result for, so I mentioned that there is this connection for the between the 2D Boussinesq equation and the 3D axisymmetric Euler equation. And we are able to also obtain some infinite in time growth result for this equation as well. So namely, our fluid domain is going to be a periodic annular cylinder. So I'm showing you on the right-hand side the one period of such cylinder, and then we just periodically extend it, right? So if we look at one period itself, then it's a compact domain, and our result is as follows. So as long as we start with large annular velocity here on these set that is colored in red, and in the part that is colored in green, we assume that on this plane, it has small angular velocity. Okay, and also the whole equation is in the axisymmetric setting. So the initial condition is also axisymmetric. Then, interestingly, as we are running the 3D Euler equation from this initial data, it's well known that the kinetic energy of this equation will be conserved, which means that the L2 norm of the U will be conserved for all time. This is well known, but we show that in terms of the velocity itself, it will be growing linearly, and as a result, it means that the fluid needs to have a very rapid change in some small neighborhood. So the vorticity will be growing super linearly as time goes to infinity. So this kind of phenomena is called the secondary flow, which means that the main direction is this big swirl here, but immediately that so this kind of flow will be generating some secondary flow in the perpendicular direction. And basically, we showed that, well, as time goes to, as long as the solution managed to survive, as long as it doesn't blow up, then this secondary flow actually will get arbitrarily strong in this sense here, as time goes to infinity. I would highly suggest for those of you that are not working on PDEs, so it's an interesting phenomena that how you can observe these secondary flow in a teacup. So if you go to YouTube and then search that secondary flow in the teacup, then you will see that, well, as you are putting the tea leaf in the teacup and then giving it a swirl, then once the water finally calms down, the tea leaves are all concentrating, not uniformly distributed at the bottom of the teacup, but they're always like in the center of the teacup. Okay, so the mechanism of this is actually because of the similar reasoning as here. The main flow is going one direction, but such flow is immediately generating some secondary flow in the perpendicular plane, and that is pushing the tea leaves towards the center. Yeah, overall, I would say that our main goal is to use some soft arguments to try to exploit certain monotone and conservative quantity in order to get the small scale formation of the 2D Boussinesq and the 3D Euler equation. With that, I conclude my talk, and thank you for your attention.
Thank you very much for interesting talk, Yao. Are there any questions or comments from the audience in person?
Hello.
Hello.
Yeah. Thank you for the nice talk. I have a question. You had an assumption on the density diffusion.
Yes.
So without density diffusion, you had this result. Anything is known with the density diffusion? What happens?
Yeah, that is a very good point. It's also a natural setting to study the case where the density also has a diffusion coefficient. In this case, what happens is that so the solution will still be globally well posed, and as time goes to infinity, the density itself actually will be converging to a constant. So for that reason, as time goes to infinity, it's like the density just sort of disappears, right? It's just converged to a constant, so that if the U equation also has diffusion, then it's known that the whole thing will just be converging to a constant density, zero velocity. And then if U doesn't have diffusion, it will be converging to the Euler equation.
And just one more question. In the compressible fluid case, anything is known?
Yeah, that's a good point. I don't think that there has been, let's see, in the compressible case, so I think that it's quite possible that for certain initial data, there will be a finite time blow up forming, right, in the terms of a shock. If there are no shocks, then I don't know whether there are any results showing that there are certain norms can grow. Yeah, so yeah, that's a very good point. I don't know what is known in the literature.
Are there any questions?
So this Boussinesq equation, does it have some conserved quantity? You mentioned kinetic energy at some point. What are the other conserved quantities?
Yes. So there is one monotone quantity, which is the total energy is monotone. And then the other conserved quantity is that because we are assuming that rho does not have diffusion, which means that the density rho is just transported by an incompressible velocity field. So in this case, all the LP norm of rho are conserved. Yeah, I think that is the only.
These are all, or there are some?
Yeah, and not only just LP norm, but like all the, let's say, the distribution of rho is conserved, right? Because the velocity field is shifting it around. Yeah, I think these are all the conserved quantity that we know.
Thanks a lot. Thanks. Thanks for the wonderful talk. Thank you.
Are there any from the online audience? Yes, she requests the presentation slides. Anyway, I have one question. Sorry, I'm not familiar with this topic, but in your first theorem, you got the estimation t to the -1/6. And how do you get it? So what is the -1/6?
Oh yeah, right. So the power is coming from it's coming from basically this key lemma here. Okay, so if we are assuming that there are no growths at all in the H1 norm, then we get that because the this H dot -1 will be so from here in this integral here, if this whole integral grows like t to the 1/2, then the integrand needs to have certain decay like t to the -1/2, and that gives that the H1 norm actually will have a certain power of growth. So that is where the contradiction come out. And then if we adjust this to have a more to have a stronger assumption that not only the limb soup is infinity, but the limb soup is like it's growing like a certain power, then all of these powers are going to like this integral will have a bigger power, so that this will change the power here. But this lemma is like a universal thing. So then if we feed that slightly bigger power into this lemma, there could still be a contradiction. And finally, like at the 1/6, this is where the assumption power with the one that we can conclude from this, the two balance each other, which means that above that, we are not able to get a contradiction anymore.
I got it. Thank you very much.
Thank you.
Are there any other? If not, please, let's thanks to the speaker again.
Thank you. And I hope you enjoy lunch and the rest of the conference.